Hello everyone, this is Ashutosh Tiwari. I am a professor of material science and engineering at the University of Utah. Today in this lecture, I will teach you about the units and measurements. The first topic that I would like to start with is the introduction to measurements and SI units. What is measurement? Measurement is the comparison of a physical quantity with a standard unit. For example, suppose you want to find the length of some object, then what you will do, you will take a scale and you will compare that object with a scale and find out how long it is. So every measurement will have two things. The first one is a numerical value and second thing will be the unit. For example, suppose the length comes out to be 5.2 meters. So 5.2 is the numerical value of that length and meters is the units. Units are of two types. The first one is a base unit and the second one is called derived units. Base units are defined for fundamental quantities like length, time, weight, etc. While derived units are the combination of base units. For example, for representing the velocity or speed of something, we will combine two base units, meter and second. So the unit for the speed will be meter per seconds. So let us look into the historical systems which were used for units. There are three such systems. The first one is called a CGS system, which represents centimeter, gram and seconds, each of these CG and S. And then there was a system called foot pound second system, where the length is measured in foot, weight is measured in pound and time is second. And then came MKS system, where the length is measured in meters, mass in kilograms and time in seconds. So these different systems were used in different countries, different geographical areas, and so there used to be a lot of confusion, and now all of those have been replaced by SI system for international consistency. So in SI system, which is a global standard, there are 7 base units. So this SI system was adopted in 1971 and it was revised in 2018. So it is the widely used systems for units, and in SI system there are 7 different units. They represent 7 different quantities. On the left hand side of this table I have shown the quantities like length, mass, time, electric current, temperature, amount of substance and luminous intensity. And on the second column I have shown the units which are used to represent each of these quantities. For example, in SI system you will represent length in meters, mass in kilogram, time in seconds. Electric current in ampere, temperature in Kelvin, and amount of substance in mole, and luminous intensity in candela. In the third column I have shown the symbols for each of these units. In addition to these 7 units, there are 2 more units in SI system. They are to represent the angles. For plane angle, suppose in a plane you have angle between 2 lines, they will use a radian, and for solid angle in 3-dimensional system that angle is used in the units of steradian. So both of these angles are dimensionless quantities. So with this, now let us move to a second topic of this chapter, significant figures and precision. Significant figures represent the precision of a measurement. For example, the world record for the 100-meter race is 9.58 seconds. So here you see in this number there are three significant figures which are 9, 5 and 8. Here 9 and 5 are called certain digits and 8 is called uncertain digits. So it means when you say the time is 9.58 seconds, then the last digit is uncertain. It can be 9.57 or it can be 9.59. Okay. Similarly, the world record for the high jump is 244.9 centimeter. So again, here you see that the last digit 9 is again uncertain and rest of the digits are certain. So all certain digits plus first uncertain digit are called significant figures. So in the case of this 9.58 second, there are three significant digits 9, 5 and 8, while in the case of 244.9 there are four significant digits which are our old 244.9. So in this way, this represents how precise a measurement is. Okay, so now I will tell you about some rules which are used for counting significant figures in a given numbers. Rule number 1 is that all non-zero digits are significant. For example, if you have a number 238 centimeter, then all digits are non-zero, so it has three significant figures. Second rule is zeros between non-zero digits are significant. So here in this number 2.308 centimeter, you see even though there is one zero, but it is in between non-zero digits, so this is also significant. So this number has four significant digits. Rule number 3 is that if the number is less than 1, the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. Let us look into this number. Here what you are seeing in this number, that there is a zero which is to the right of this decimal point but to the left of any non-zero number which is 2. So this 0 in this particular case is not significant. So this overall, this number 0.02308 has only 4 significant digits. Rule number 4 is that trailing zeros without a decimal point are not significant. In this number 123,000 millimeter, you see there are 3 significant figures. The remaining these 3 zeros which are trailing are not considered as significant figures. Then the rule number 5 is that trailing zero in a number with a decimal point are significant. So if you write a number like 3.500, then here all zeros are also significant. So it has 4 significant figures. So if you are writing 3.500, then one would understand that your precision is up to the last digit 3.500. So your last digit is up to that point your measurement is precise. For any reason, suppose you want to put some more zeros after that, that is not allowed. You cannot put any more zeros after that, because when you write these numbers in certain way, that represents how accurate, how precise your measurement is. So it is very important to be very careful about finding out significant figures. So now the examples of numbers we discussed here in this previous slide were in standard decimal notation. But in this notation, the significance of trailing zeros can sometimes be ambiguous. Let us look into the example. For example, suppose you found a length as 4.700 meters. You did some measurement and you found that object is 4.700 meters. So in this number, there are 4 significant figures, 4, 7, 0 and 0. Now suppose we change the units. We change these meters to millimeter. So we can write 4.700 meter same as 4700 millimeter. The number 4700 millimeter may appear to have just 2 significant figures based on the rules which we learned in the last slide. Right? We saw that trailing zeros are not significant. But that would not be correct in this case, because when you convert the unit, the significant figures should not change. But here, because of this ambiguity, it is changing. To remove this ambiguity, often scientific notation is used. Instead of this simple decimal notation, it is custom to use a scientific notation for most of the scientific work. So in scientific notation, every number is expressed as a into 10 to power b, where a is the number between 1 and 10, while b is a positive or negative number, that power 10 to the power b is any positive or negative number. This formatting removes the confusion about trailing zero. For example, 4.700 meters, if I want to convert it to centimeter, I will just write 4.700 and 10 to power 2 centimeter. Similarly, if I have to write it in millimeters, I will just keep 4.700 and 10 to power 3 millimeter. And similarly, you can do in kilometers, 10 to power minus 3. So you see the number of significant figures remains the same. The power of 10 here is irrelevant to determining the significant figures. What matters is the base number a, which is all the time is having same number of significant figures. So that is why this scientific notation is very widely used. It helps in avoiding ambiguity when we present our results. Another quantity I would like to introduce at this point is the order of magnitude. In some cases, we need to just compare how two quantities relate in a rough sense. We don't want exact numbers, just rough, that how they compare. What matters in such situation is not the exact value, but the order of magnitude, that how they compare. And for doing such estimation, we assume that if a is less than or equal to 5, we round it a to 1, and if a is between 5 and 10, we round a to 10. So in this way, the quantity is then approximated as 10 to power b, and the exponent is called the order of magnitude. Let us look into the example. The diameter of the earth is 1.28 into 10 to power 7 meters. If you round it, it will be 1 into 10 to power 7. So this 7 will be the order of magnitude. Now another example is a tennis ball. A tennis ball has a diameter of 6.7 into 10 to power minus 2 meter. If you round 6.7 to 10, then this diameter will come out to be 10 to power minus 1 meter, and so the order of magnitude will be minus 1. So this is a very useful thing when you have to make some rough comparison. Okay, so now we will look into what happens to significant figures when we perform a certain arithmetic operations. When performing calculations with measured values, the result cannot be more accurate than the least precise measurement. So, this is the rule of thumb. When performing calculation with measured values, result cannot be more accurate than the least precise measurement. Using too many digits in final results can give a false impression of accuracy. When you are doing certain calculation using your calculator, you may end up with lots of digits, and that may give an impression that your measurement is that accurate. So, that should not be done. So, now let us look into the arithmetic operation of multiplication and division. The rule is the final result should have as many significant figures as the value with the least number of significant figures. So, we will learn understand this rule with the help of following example. Suppose the mass of an object is 4.237 grams, and as we have already learned how to find significant figures, we can see that it has 4 significant figures, 4, 2, 3 and 7, so 4 significant figures. Volume of the same object is given as 2.51 centimeter cube. It has 3 significant digits, 2, 5 and 1. Now, suppose you are asked to find the density of this object. So, what you will do is simply divide the mass with volume, and you will end up with a number in your calculator something like this, 1.68804781. So, if you write this number, then somebody will have an impression that the accuracy of your measurement is till this last digit 81, which is actually not the case. So, you need to round this number to just 3 significant figures, because the volume which you had 3 significant figures. So, the rule is the final result should have as many significant figures as the value with the least number of significant figures. So, volume has the least significant figures 3, so density will also have 3. So, you should write your answer as 1.69 gram per centimeter cubes. Now, coming to addition and subtraction. In the case of addition and subtraction, the rule is the final result should have as many decimal places as the input with the fewest decimal places. So, we will understand again this rule with following example. Suppose you have 3 numbers. First one is 436.32 gram, second is 227.2 gram, and the third one is 0.301 gram. And you are asked to sum all these numbers. Then if you use simple calculator, you will get sum as 663.821 gram. But this will be the wrong way of writing your result, because the final result should have as many decimal places as the input with the fewest decimal places, and the fewest decimal places are in this case 227.2 and only 1 decimal place. So, it is not right to write your result with so many numbers after decimal. You should write only till 1 decimal point. So, it will be 663.8 gram. Let us look into another example, which is about subtraction. If you are subtracting 0.307 and 304 from 0.307, your number should be 0.003 meters. You can also write it final result as 3 into 10 to power minus 3 meter. But you cannot write it as 3.00 into 10 to power minus 3 meter, because if you write in this way, it would imply more precision than the data supports. Your experiment is not that accurate. so that you can write these zeros after that thing. Now I will also give you some tips for rounding off the numbers, the right way to do this thing. For example, suppose you have a number with 2.746. So now if the last digit is more than 5, we round it up, because in 2.746 last digit 6 is more than 5, you should write it, you can write it as 2.75. On the other hand, if the last digit is less than 5, then you should drop it. For example, in 2.744, the last digit is 4, so if you want to round it, you have to drop it. So it will be 2.74. Now comes a very tricky situation. If the last digit is exactly 5, then what to do? So then there is the following convention is that if the last digit is just 5, we look into the second last digit with the digit before the last digit. And if that second last digit is even, you should drop the last digit. So for example, 2.745, the second last digit is even, so you should drop this 5 and it will be 2.74. On the other hand, if second last digit is odd, which in this number 2.735, then in this situation you should round it up. This 2.73 should become 2.74. So these are the normal conventions which are very often used in scientific research. So you should follow these rules. After you have learned about the rounding, how to round the numbers, I would like to give you some tips about a multi-step calculation. When you are doing multi-step calculations, one after the other, then it is always important to keep an extra digit in the intermediate steps. If you round too soon, you introduce rounding errors. And so this simple trick which I am telling you will keep your final answers accurate. For example, suppose I am dividing 1 by 9.58 and the number is, I just round it early and then I write it 0.104, which is basically correct if I have just one step, because this number has 3 significant digits and this also has 3 significant. But because we are doing multi-step calculation, there is another step after that, so you should not do it. Rather, you should write 1 digit extra than these significant digits. Otherwise, what will happen, suppose in the next step I just divide 1 by 0.104, then your answer will be 9.62, which is not the same which was in the beginning. On the other hand, if you had used 1 digit extra and if you divide it, it will be 9.58. The wrong way gives you an incorrect value. Even though it looks okay, the right way keeps extra digit until the end. So this is the right way of doing. They always keep an extra digit in the intermediate steps. And at the end, very end, you can round it completely. So now with this, I would encourage you to try these examples and write your answers in a comment. The first question is to find the density, which is by dividing mass with volume. Write your answer with significant digits, write significant digits. Second one is subtraction, 12.9 grams minus 7.06 gram. Again, write your answer with right number of decimal places and then find the volume of something which has a cubic dimensions 7.203 meter cube, and write your answer with significant correct number of significant figures. Now we will move to topic 4, which is on errors and uncertainty. Every measurement involves some error. No instrument is perfect. No matter how accurate instrument you get, there will always be some error in the result which you get. So errors are of two types, can be classified in two types. The first one is absolute error, and second thing which is related to the absolute error is a relative error. Suppose you are measuring the length of an object and the length comes out to be say 16.2 centimeter. Then the last digit is all the time uncertain, point is 2 digit is uncertain, and this can be uncertain by 0.1. So 16.2 can be 16.1 or it can be 16.3. So the error, the absolute error in this quantity is plus minus 0.01 centimeter. Now if you have to find the relative error, then what we do is we divide this 0.1 by 16.2 and then we multiply by 100. So it comes out to be 0.6%. So the absolute error is the uncertainty in the measured values, where it is in this case is 0.1 centimeter, and then if you divide it by the value itself and multiply by 100, you get relative percentage error. So it is always a good idea whenever you do any experiment, you do any measurement, it is always a good idea to find out how accurate, how much is the uncertainty in your measurements. Relative error depends on the value. For example, suppose you have 1.02 gram weight measurement and the error was 0.01 gram, absolute error. Relative error will be 0.98%. On the other hand, suppose your mass was bigger, then for the same absolute error, your relative error is less. So smaller quantities with the same absolute error have larger relative errors. That is why precision becomes more important when dealing with small values. When you are dealing with very small quantities you are weighing, at that time your precision should be very high. Otherwise you will make big errors in your calculations. So now let us say how the errors propagate. When we do multiplication or division, relative errors add up. Let us say length of an object is 16.2 with an uncertainty of 0.1 centimeter and breadth is 10.1 centimeter, again with an absolute error of 0.1 centimeter. Now if I find the area of this with this length and breadth, then you simply multiply length and breadth and then you come up to 163.62 centimeter. Now let us look into the relative errors. In the case of length, relative error is 0.6%. In the case of breadth, relative error is 1%. Again, simply you are dividing 0.1 by 10.1 and it comes out to be 1%. So total area error in this area will be the addition of these two relative errors. So it will have an error of 1.6%. So if you have to write the area can be written as 163.62 centimeter square plus minus 1.6%. And now if you convert this 1.6% into the real number, it is 2.6 centimeter square. Now if you have to report it, you should report something like this: 164 plus minus 3 centimeter square. So this is the right way to report your results, which are done after multiplication of experimentally measured numbers. Now in addition and subtraction, we do not combine relative errors, rather we match a decimal places. For example, suppose you are subtracting 12.9 from and 7.06 from 12.9, you get a number of 5.84. If you write 5.84, this will be the wrong way of writing, because you are seeing that in 12.9 there is only one decimal place. So answer should be rounded to one decimal place. We have already discussed this in previous slide also. So your number which we will report in the correct format will be 5.8 grams. So rule is match least decimal places. So now just to recap about errors and uncertainty. Absolute error means the uncertainty in the value. Relative error means error divided by the value. Relative percentage error means relative error times 100. In multiplication and divisions, add relative errors, and in addition and subtraction, match decimals. And one thing you should always keep in mind on all these operations is that you should round numbers only at the final step. Okay, so in the intermediate step, you don't round it. Rather, you keep your significant digits plus one extra digit. Otherwise, there can be rounding errors. Now coming to the last topic of this chapter, which is on dimensional analysis. Let us first ask the question, what are the dimensions? In physics, dimension refers to the physical nature of a quantity and is expressed in terms of basic measurable units, which we call a fundamental or a base quantities. For example, length has the dimension of L. Time has the dimension of T, and mass has the dimension of M. When we combine these base quantities to describe other physical quantities, we define their dimensions. For example, velocity is distance divided by time. So its dimension will be L t minus 1. L for the distance, and because it is divided by time, so t to the power of minus 1. Similarly, the force is defined as the mass time acceleration, and the dimension for mass is m, while for acceleration it is L t minus 2. So the dimension of force will be m L t minus 2. Coming to dimensional formula and equation. A dimensional formula expresses the quantity in terms of the powers of the base units. For example, volume can be written as m to the power of 0, L to the power of 3, and t to the power of 0. Similarly, the speed, which we discussed earlier, can also be represented as m to the power of 0, L to the power of 1, and t to the power of minus 1. And force can be represented as ml t to the power of minus 2. A dimensional equation simply sets this formula equal to the symbol of the quantity. For example, the dimensional equation for volume, speed, and force may be expressed as V m0 L3 T0. Then velocity, small v, has the dimensions of m to the power of 0, L to power 1, and t to power of minus 1. And force has m L t minus 2. So these are called dimensional equations. There is a principle called principle of homogeneity. According to this principle, every term in a physical equation must have the same dimension. For example, if one term has a dimension of L, all other should also have the same dimension. Let us look into the example. Here is an equation which is x equal to x naught plus v naught t plus half at square. Now let us check each term. x0 is the distance, has a dimension of L. v0t terms. v0 is the velocity, so it has a dimension of L t minus 1, and small t here represents the time, which has a dimension of t. So when you combine all these dimensions, the dimension of v0t also comes out to be L. Now looking into the third term, half at square. A is the acceleration, so it has a dimension of L t minus 2, and t square has a dimension of t square. So if you combine all these things together, you come up with length L. So we see all terms here have same dimension L, so this equation is dimensionally consistent. If suppose there was it was not true, some terms were not having the same dimension, then you can say that equation is dimensionally incorrect. So it is very good way to check the validity of the equation, whether some equation is correct or not. If it is dimensionally incorrect, then it means equation will be incorrect. So let us verify a real equation, which is kinetic energy equal to potential energy. So equation for kinetic energy is half mv square, and for potential energy it is mgh. So let us see whether dimensions are consistent or not. On the left hand side, mass has a dimension of m and velocity has Lt minus 1. When you square it, it will become L square t to power minus 2, and when we put it together, the dimension of left hand side is m L2 t minus 2. Now let us look into the right hand side. Right hand side has mass and then acceleration due to gravity and height. Dimension for mass again is m. For acceleration due to gravity is L t minus 2, and height has a dimension of L. So if we combine all these things together, we again end up to m L2 t minus 2. So both sides simplify to m L2 t minus 2. This confirms that equation is dimensionally valid. In this way, you can check any equation and can verify whether that equation is correct. So now I will show you how you can use this dimensional analysis to derive some simple formulas. So let us take the example of pendulum and derive the time period of a pendulum using this dimensional analysis. For this, the first thing that we will assume is that time period t is given by a following expression, where k is a constant, L is the length, g is the gravitational acceleration, and m is the mass. So time period of a pendulum is k times L to the power of x, g to the power of y, and m to the power of g. Now let us look into the dimensions both on the left hand side and right hand side. Left hand side, the dimension is simply t. On the right hand side, we have to put the dimensions of all these individual quantities like length, g, and mass, and appropriate a power. So L to the power of x times L t to the power minus 2 whole to the power of y, and then m to the power of z. If we simplify, on the left hand side it remains t, while on the right hand side you see L to the power of x plus y, t to the power of minus 2y, and m to the power of z. Now match the dimensions on both the sides, because length on the right hand side is x plus y, on the right hand side is x plus y, on the left hand side you have 0. Similarly, when you compare the dimensions of t, you get minus 2y equal to 1, which gives y equal to minus half. And then m to the power of z, and there is no m on the left hand side, so z equal to 0. So if you simplify these simple equations, you get x to the power of x equal to half, y equal to minus half, and z equal to 0. So now let us put back all these numbers in this first equation, and we get t equal to k to times l to power half and g to power minus half, which can be written as k equal to t equal to k times under root l by g. And we know that for the pendulum, that period is given by this similar expression. What are the limitations of dimensional method? While useful, dimensional analysis has limits. For example, it cannot give dimensionless constants like 1 by 2 or 2 pi. For example, in the derivation of time for pendulum, we could not find the value of k, the constant, although we could find all other quantities, but that dimensionless constant cannot be figured out. It cannot distinguish between quantities with same dimensions and does not apply to non-algebraic functions like sine or log.